Welcome to Yaka Digital Network. If you accidentally touch a pot of boiling water at 100 degrees Celsius, you get a nasty burn. But if your hand catches the steam rising from that same pot, also exactly 100 degrees, the burn is significantly more severe. To understand why, we need to look at exactly how heat energy interacts with matter. We measure heat in two distinct ways. On the left, heat capacity is the energy needed to warm up an entire object by 1 degree. A massive pot of water requires far more heat than a tiny metal cup. On the right, specific heat capacity normalizes this to exactly 1 kilogram of material. Different substances heat up at different rates. A kilogram of water takes much longer to warm up than a kilogram of cooking oil. As long as you are raising the temperature of an object, you can calculate the exact energy added using this formula. Q equals mc change in theta. Q is the heat energy, m is the mass in kilograms, c is the specific heat capacity, and the triangle theta symbol represents the change in temperature. This mathematical rule reliably tracks the energy you add minute after minute on the stove, but it has a strict limit. The moment that water begins to boil, this formula breaks down. This heating curve graph illustrates what happens next. The rising orange line shows the temperature increasing exactly as our formula predicts. But when the water hits 100 degrees Celsius, the line plateaus entirely. The fire is still burning, adding continuous energy, but the temperature flatlines. The graph levels off because the water has reached its boiling point. The thermal energy is now acting as the specific latent heat of vaporization. Instead of making the liquid hotter, this hidden energy is being consumed to completely break the molecular bonds holding the water together, allowing the molecules to fly apart as steam. This resolves our opening mystery. Steam burns are far more damaging because steam carries all of that massive, hidden, latent energy. When it hits your cooler skin and condenses back into liquid water, it dumps that extra bond-breaking energy directly into your tissue. When dealing with phase changes, thermal energy physically alters the state of matter rather than increasing its measured temperature. You have to put away the temperature change formula and switch to measuring the latent heat. Turning water into gas rapidly requires hitting 100 degrees on a stove. Yet farmers successfully dry freshly harvested crops, and we dry our laundry outside at normal room temperatures. This comparison table breaks down the two entirely different mechanisms for vaporization. Boiling is a rapid, bulk process that happens throughout the entire liquid at a fixed temperature. Evaporation, however, is a slow process that happens only at the exposed surface of a liquid, and it can occur at any temperature. If you are designing a solar dryer for maize or beans, stacking the crops in a thick layer won't help. Because evaporation happens exclusively at the surface, spreading the crops out flat maximizes the exposed area, directly increasing the rate at which water molecules can escape into the air. A boiling pot relies on a heat source to force a phase change, but evaporation is driven simply by surface area exposure and the natural kinetic energy of the individual molecules. Even with plenty of surface area, evaporation faces an environmental constraint, dictated by the air around it. In physics, we track this using saturated and unsaturated vapors, what we typically call humidity. Look at the shoreline of Lake Victoria on a cloudy, rainy day. If you hang wet clothes outside in Kampala under these conditions, they will take hours or even days to dry. The air near the lake is already holding its maximum possible capacity of water vapor, making it a saturated vapor. As water molecules evaporate from your wet shirt, an equal number of atmospheric water molecules condense and return to the fabric. The rates of evaporation and condensation are in perfect equilibrium. Your clothes dry quickly on a sunny, unsaturated day because the air is dry. A vapor's ability to form is entirely dependent on how much moisture the surrounding environment can accept. Let's apply the math. Pause the video and calculate the heat supplied to a 2-kilogram block of iron heated from 20 degrees Celsius to 70 degrees Celsius. Use a specific heat capacity for iron of 460 joules per kilogram Kelvin. Here is the step-by-step working. You multiply the mass of 2 kilograms by the specific heat of 460, and then by the temperature difference of 50 degrees. The total heat supplied is 46,000 joules. This cutaway diagram of an insulated copper calorimeter illustrates how we measure energy transfer in a lab. The master rule here is the principle of conservation of energy. If you drop that hot iron block into cold water inside this container, the exact amount of heat lost by the hot iron is equal to the heat gained by the cold water. Whether thermal energy is raising a material's temperature, breaking molecular bonds during a phase change, or transferring between objects, the total amount of energy in a closed system is always conserved. This final cheat sheet summarizes the three primary tools for calculating heat quantities. Use Q equals mc change in theta for temperature changes, use Q equals ml for latent heat during phase changes, and remember that heat lost always equals heat gained. Thank you for learning with Yaka Digital Network. Be sure to click on the next lesson on your screen and visit us at www.yaka.cc for more interactive courses.